So back in 2006, the world of artificial intelligence was, well, it was kind of stuck. Then this one research paper comes along from Geoffrey Hinton and his team with an idea so powerful it just completely broke a years-long logjam. And in doing so, it basically kicked off the whole AI revolution we're seeing today. No joke.
And that was the million-dollar question, right? I mean, everybody knew that deeper networks, with more and more layers, should be smarter. But when you actually tried to build them, total disaster. They just wouldn't learn. So what was the secret?
All right, so here's how we're going to break this down. First, we'll get a handle on why deep networks were such a problem. Then we'll meet the main villain of our story, this weird issue called explaining away. After that, we'll dive into Hinton's brilliant solution, see how they fine-tuned it, how it just blew everything else out of the water, and then, the coolest part, we'll actually take a peek inside the AI's mind.
Okay, so first things first, let's set the scene. We're in the early 2000s, and adding more layers to a neural net, it just made things worse. Which makes no sense, right? More should be better. You'd think it would be simple. The first layer learns basic pixels, the next learns edges, the one after that learns shapes, and so on. More layers should mean a smarter AI. But what actually happened was that the learning signals they sent back through the network would either just vanish or they'd completely blow up into gibberish. It was a total mess. The network basically couldn't learn from its own mistakes. And for years, the culprit was this really sneaky statistical problem.
And that brings us to the big bad of this story. It's a phenomenon with an awesome name, explaining away. And you'll see it gets right to the heart of why these deep models were so hopelessly confused.
The paper uses this really great analogy to make it all click. Okay, picture this. Your whole house suddenly shakes. What happened? Well, it could be an earthquake, or maybe a big truck just smashed into it. Now, normally, those two things have nothing to do with each other. But the second your house shakes, there's suddenly rivals. Think about it. If you feel the ground shaking like an earthquake, you're not also thinking, and maybe a truck hit us too. Nope, the earthquake explains away the truck. It's a good enough reason. You don't need another one.
And that's the key idea right there. You've got two completely separate potential causes, but the moment you see an effect they could both create, they're suddenly locked in this weird competition with each other.
So you can imagine, inside a deep network, this was pure chaos. Every layer was trying to explain the data from the layer below it, and all the little features were constantly explaining each other away. It created this huge, tangled knot, and the network had no idea what to learn. So learning just stopped.
So how on earth do you untangle a mess like that? Well, this is where the genius of Hinton's paper really shines. Instead of wrestling with the whole deep network at once, they said, let's just be greedy. Let's train it one single layer at a time. And the algorithm itself is just beautiful in its simplicity. Step 1, you take your raw data, your pixels, and you just train that very first layer. That's it. Pretend the rest of the network doesn't even exist. Once it's good at its job, you freeze it, lock those weights in place. Step 2, now you take the output from that first layer and you treat it like it's brand new data, and you use that to train the second layer. And you just repeat. You just keep stacking and training one layer at a time, all the way up.
What you end up with is this completely different kind of network. Each layer is its own little self-contained module. The technical name is a restricted Boltzmann machine. That's just trained on what the layer right below it learned. By building it piece by piece like this, they just completely dodged that whole explaining away nightmare. But this was just the first phase.
Okay, so this layer-by-layer pre-training, it gave the network a really, really good head start. But remember, each layer was trained on its own. They weren't really talking to each other yet. To get them to work together like a real team, they needed one last step.
This final polish was a process they called the up-down algorithm. You can kind of think of it like finally letting all the layers talk to each other. They sent signals all the way up and all the way down, letting everything adjust to everything else. It was all about getting the whole system to work in perfect harmony.
All right, the moment of truth. All this theory is super clever, but did it actually work? Was it any good? So they put it to the ultimate test, MSIT. You know, the classic hello world of image recognition, where you have to classify handwritten digits.
And wow, did it work. It nailed an error rate of just 1.25%. Now, you have to understand, for that time, on this specific benchmark, that was an absolutely killer result.
And when you put it next to the competition, you really see what a big deal this was. It beat the best support vector machine, and back then, SVMs were the king of the hill. It also left the old-school neural networks totally in the dust.
This was huge because for the first time, a generative model, one that actually learns the structure of the data, had beaten the top discriminative models, which are just built for sorting things into boxes. That was a massive turning point.
But wait, it gets even cooler. See, because this was a generative model, it didn't just learn to recognize numbers, it learned what a number is. Which means you can ask it to, well, create one from scratch. You can literally ask it to just imagine a number for you.
Look at these. These are not real handwritten numbers. No one drew these. This is the AI, basically dreaming up what it thinks a 0 or a 7 or a 9 should look like. It's captured the very essence of each digit deep inside its own weights. It's wild. And we can even watch its thought process in action. So here on the left, it starts with total random noise, just static. And then, as it runs, you can watch it settle, refining that noise over and over until a clear, stable idea emerges on the right. It's literally like watching a thought form out of complete chaos.
This led the authors to this really profound idea. They basically said, hey, what if what we're seeing isn't just a metaphor? What if a mental state for this AI is the actual image, the external world, that perfectly corresponds to its internal idea? In other words, that picture it creates, that's literally what the network has in mind.
So, at the end of the day, this paper did so much more than just beat a benchmark. It was the key. It was the recipe that finally showed everyone how you could train these incredibly deep networks. And that just unlocked the floodgates, paving the way for the absolute AI revolution we are all living through right now.
And that just leaves us with one last big question. Think about it. This little 2006 model learned this rich internal concept of numbers from just simple black and white images. Today's giant AI models are trained on, well, pretty much the entire internet. So what kind of complex mental states are they forming about our world? And what would we even see if we could ask them to show us what's on their mind?